From our practice test C in the gas laws chapter, the gas laws in stoichiometry, we are looking at the relationship between the ideal gas law, known as PV equal nRT, the PV equals nert, and the stoichiometry, where we know that the mole is the relationship between the ideal gas law and the stoichiometry roadmap. So, as we begin, knowing that a PV equal nRT and a stoichiometry problem will both be involved as we proceed through each of our problems. Let's read through the first one that says, iron metal reacts with oxygen gas to form solid iron 3 oxide. We'll begin by writing the balanced equation. The iron metal is simply written as Fe. Reacts with is the plus sign, and the oxygen gas belongs to the diatomic molecular club, written as O2. To form is our arrow, an iron 3 oxide, written by ionic charge, Fe with its plus 3, telling me that from the Roman numeral. Oxide is a -2, so we come up with Fe2O3. When we balance our equation, we get the stoichiometric ratio. I have an odd number of oxygens on the right-hand side, so I'll know to double, giving me a 3 in front of the oxygen and a 4 in front of the iron. So we have a 4:3:2 stoichiometric ratio. When we proceed to the letter B, if an enclosure of 75 liters, sounds like a volume, has a partial pressure, so there's the pressure unit, as 2.5 times 10 to the negative 3 torr is our pressure unit. Temperature is given as 55 degrees Celsius, so that sounds like a T. Matching the R constant to the torr unit is 62.4. We're ultimately being asked to solve for the iron, but we're given information all about the oxygen, the volume of the oxygen, pressure, temperature, and an R constant related to the reactant for O2. Since I already know a volume, pressure, temperature, the missing variable from the PV-nert equation is the N, the number of moles of oxygen. With this problem, we'll PV-nert first, followed by the stoichiometry. Plugging in for what we know, the pressure unit, 2.5 times 10 to the negative 3 torr units. Volume, already provided in a liter, was 75. We're pulling out N, where N stands for the number of moles of the oxygen. R is the constant, 62.4, and the Kelvin temperature, let me add 55 and 273, and I find 328 Kelvin units. PV divided by RT pulls out N, where N will stand for the mole value of the oxygen reactant. So I will hit 2.5 E negative 3, that's our pressure, times the volume of 75, divide by 62.4, the R constant, divide again by 328, our Kelvin temperature. And I find 9.16 times 10 to the negative 6th moles of oxygen. This now begins the journey for the stoichiometry. Given the number of moles of oxygen, we can use that to get to the mass of iron. So the very answer we just found becomes the starting point for the next part of the problem. We know we have 9.16 times 10 to the negative 6 moles of oxygen. That places us right in the heartland on our stoichiometry roadmap, and I can see that there would be 2 steps to take it out to the grams of iron. So given a mole, we'll calculate a mass. We begin with the stoichiometric ratio of want over given. We'd like to know iron, its coefficient of 4 placed up on the top, set over the 3 moles of oxygen set on the bottom. So our ratio of 4/3. To bring that mole of iron out to mass of iron, we'll use the formula weight of 55.8 grams of iron in every 1 mole of iron. So on my calculator, I still have the number of moles here, 9.16 times 10 to the negative 6. I'll hit times 4/3, times 55.8 for the molar mass of iron, and I get 6.8 times 10 to the negative fourth grams of the reactant iron. With this problem, we knew pressure, volume, and temperature. We puvnert first to find N, where N stands for the moles of oxygen. That began then the stoichiometry to pull out grams. We actually used the same starting place for the letter C. If we know the number of moles of oxygen from the puvnert problem, we can also use that value to get over to the product side. The iron oxide can be determined from the number of moles of oxygen. So begin that same journey, 9.16 times 10 to the negative sixth moles of oxygen, the value of N from the puvnert problem. But now we have a new target, and that's the product, the Fe2O3. And it also says it's only a 75% efficient equation, so I'll take 75% of my answer to find the mass of the product produced. So we begin with our ratio. We want the product this time from the oxygen. We have 2 moles of Fe2O3 set over the 3 moles of O2, a 2/3 ratio. Let me add a molar mass of our product, Fe2O3, 55.8 times 2 for the iron, plus 16 times 3 on the oxygen, and I come up with 159.6 grams in every 1 mole of our product. Alrighty. So the N value from the puvnert, the number of moles, begins the part C. I will hit 9.16 E negative 6 times 2 over 3 times 159.6 and times 0.75, giving me that 75% efficient equation. I'm finding 7.31 times 10 to the negative fourth grams of Fe2O3. When we know the volume, the pressure, the temperature, all 3 of those provided, that's our clue to puvnert first. In our second example, I believe it's the opposite direction. Let's take a look. Write the balanced equation for the combustion of liquid octane, and each product is gaseous. So we'll begin with a little combustion pattern. C8H18 is octane. We will add oxygen. Out comes carbon dioxide and water vapor. When I balance a combustion, my strategy is to always start with C's, then H's, and leave the O's for last. When I count on the left, I see 8 carbons, so I'll place an 8 in front of the carbon on the right. I'm counting 18 hydrogens, so I place a 9 to balance the H's. And now when I take a look at the product side, I ended up with an odd number of the oxygen. And there's no way I can balance an O2 with an odd number. So everything we figured out goes back and gets doubled. 2 in front of the octane gives me a 16 in front of the carbon dioxide. A 2 in front of the octane makes me put an 18 in front of the water. And now let's count the total number of oxygens on the right. 16 times 2 from the carbon dioxide and 18 more gives me a total of 50 oxygens, so I can place a 25 in front of my O2. A 2 to 25, 16 to 8 coefficient ratio. The letter B says, what is the volume of oxygen gas measured at 150 degrees Celsius and 2.725 atmospheres when I need to react 50 grams of octane? Well, if we're looking for a volume, I know a temperature, I know a pressure, I can match the R constant, 0821, and I certainly don't know moles yet. There's too many variables left open in the puvnert equation. If I'm looking for a volume, that's my clue that says, don't do a puvnert first. Start with the stoichiometry. Start with the 50 grams of octane and find the number of moles of oxygen. If we can make the N, the oxygen moles, our target, we could then PUV-NERT. So stoichiometry first, followed by the PUV-NERT problem. So the reactant provided was 50 grams of C8H18. It's a two-step conversion where I'm trying to find moles of oxygen using that value for the N in the PUV-NERT problem. So I'll need a molar mass in my first conversion. I'll add together C8H18. 12 times 8 for the carbon plus 18 more on the hydrogen, and I get 114 grams as the molar mass. We go to the heart of our problem next, the want over given ratio. We want to know the oxygen. Its 25 coefficient gets placed on the top, set over the 2 moles of the octane, C8H18. We have our 50 grams want over given ratio brings us out to the moles of oxygen. 50 divide by 114 times 25 divide by 2, and my calculator says 5.48 moles of O2. That becomes the N when we PUV-NERT, pulling out then for the value of the volume. Step 2 says, now that we have moles of oxygen, let's PUV-NERT. We know the pressure unit was given as 2.725 atmospheres. Let's find the volume. N was just determined, 5.48 moles. R is the gas constant to match an atmosphere, 0.0821. And the Kelvin temperature of 423. Alrighty. We know pressure, we're solving for volume, we know mole, we know the constant R, and the Kelvin temperature. Start on the side that does not contain the variable, so nRT divide by V, and we will find liters of oxygen. So I'll hit 5.48 times 0.0821 times 423, and I'll divide by 2.725. And I found 69.8 liters of oxygen. With the letter C that accompanies this same equation, we're being asked to solve for the volume of each of the products as well. So we again started with the 50 grams of octane, and we moved to oxygen. Now we'll move to carbon dioxide, and then again